introduced, my name is Zhang, and I'm a first-year PhD student from Carnegie Mellon. Today, I'm going to talk about the project called Tomo. It is an electrical impedance tomography system. In this project, we used it for hand gesture sensing. As you know that smartwatches are increasingly being used because they are small, wearable, and powerful. However, the touchscreen on it is so small, where our fingers are so big, which makes even the basic manipulations quite difficult. In comparison, our hands are very expressive. We can bend our wrist and manipulate our fingers to make many hand gestures in everyday communication. So we wondered, can we develop a technique for smartwatches that can allow hand gestures to work together with touchscreen? Many possible solutions have been tried. For example, we can attach accelerometer and gyroscope to the fingers. We can also detect contour changes of the wrist skin. Or we can have a camera to look at the hand directly. Note that all these technologies look at the outside of a user's body. There is a popular method that does measure the inside of a user's body, that is EMG, which measures the muscle activation. In this work, we explored a different technology that also looks inside a user's body. It is called Electrical Impedance Tomography, which is quite new for the HCI world, but is well known in industrial and medical fields. We can apply this sensor to a user's arm and detect muscles changing their cross-sectional shape with different hand poses. Based on that data, we can perform the hand pose classification. Before we go into details, let me talk more about what tomography is. Tomography techniques insert excitation signals to a series of points from outside of an object. When the signal travels through the object, it is attenuated and distorted because of the interior. So based on that data, we can reconstruct an estimated interior image of the human body by using some algorithms such as back projection, which is also used in Tomo. One example we are familiar with is magnetic resonance imaging, which rotates around our head but can get an image of our brain. Note how high resolution the reconstructed image is. There are many tomographic techniques. Even though they share largely the same sensing principle, the excitation signals they are using are quite different. For example, MRI uses magnetic fields, while CT scan uses X-ray, PET scan uses gamma rays. Electrical impedance tomography, on the other hand, uses electrical current as its excitation signal, but the idea is similar. However, the version we built is much smaller and cheaper, which allows this technology to be integrated into something like a smartwatch. Now, let me explain how Tomo actually works. The simplest electrical impedance sensing system uses a single emitter and one receiver. The emitter outputs a high-frequency AC signal, while the receiver measures the amplitude of that signal. This captures the impedance between the two electrodes. Since one data doesn't tell us quite much, we add more receivers. This way, we can measure impedance along different paths through the object. And we can also multiplex the transmitter and the receiver to create more combinations of the paths. With enough data, we can reconstruct an estimated 2D image of the interior of that object. Here is a simple demo for a bath of water that we have surrounded with our electrodes. On the right side of the laptop screen is the row pairwise impedance value, while on the left side of that laptop, we show the reconstructed image. If we dip in a cylinder made of plastic, we can see a red dot appear on the visualization, which indicates an object of high impedance. And then, if we dip in a piece of metal which is low impedance, we can see a blue dot on the visualization. That's the location for the low impedance object. Now, I'm going to try a live demo, but this time on my arm. Okay, let me first explain what is going on that canvas. So along the top, we have the raw pairwise impedance value measured from all pairs from the electrodes. On the bottom right, we visualize the same data, but in a more structural way, that is a mesh. So on the bottom left, we can see the reconstructed image of my arm's interior. Since the muscle movements is quite minor, it's very difficult to see. We also visualize a difference image in the middle to make it easier to see. Now, what I'm going to do is I will train 5 gestures and test them live. So now let's define this gesture to be relax. Relax, 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 relax. Now, down, up, index pinch, and Spider-Man. Okay, let's do one more round. Relax, down, up, index pinch, and Spider-Man. Okay, train the classifier. The result will be shown on the screen shortly. Okay, now I'm gonna perform a down gesture. So next, let's do up. Okay, now let's do Spider-Man and index pinch. As we can see, even with such little training data, the classifier still works quite well. Down, up. Okay, that's my live demo. So here is a close-up of the Tomo sensor board. It has 3 key components: 1 network analyzer impedance sensor and 2 multiplexers. This circuit board and its all components could cost under $10 if produced in volume, and is very likely to be integrated into a single chip in future. So here I will talk about the schematic of Tomo. In total, the system has 8 electrodes. It is built around 1 network analyzer chip, which can measure the impedance between 2 pins. We configured the excitation signal to be 40 kilohertz with 400 millivolts peak to peak. This signal is then multiplexed by 2 multiplexers to select any 2 of the electrodes to be the transmitter and receiver pair. So 8 selecting 2 without repetition gives us 28 possible measuring paths. Note that this chip can perform an on-chip FFT. It takes roughly 1 millisecond to collect enough data and 2 milliseconds for the computation. So give over 28 pairs, we can achieve about roughly 10 frames per second. Okay, here is what the entire Tomo setup looks like. We use an Arduino Mini to interface with the sensor board and send data over Bluetooth. The entire setup is powered by a lithium polymer battery. Here is a new version of a Tomo setup. That is what I'm wearing right now. So as we can see, it's much smaller and more integrated. Everything is integrated into one single PCB. So once the data is sent, Tomo computes the image of the interior that best matches the observation. We calibrated each of the 28 paths with a 10K resistor to have a better measurement accuracy. We use a MATLAB toolbox with linear back projection to reconstruct the image. In order to see how accurate Tomo is, we run a 10-participant user study. We used 2 gesture sets, which I will talk about on the next slide. Even though we designed our technique for smartwatches, it is still interesting to see how Tomo can work on different arm locations. So in the study, we tested under 2 wearing positions, that is wrist and forearm. Please refer to the paper for more procedural details. Before I go into detail about the evaluation result, I want to briefly talk about how about the 2 gesture set we included in the user study. In order to compare our result with previous work, we adopted a widely used pinch gesture set. This includes relaxed, middle, ring, and the little finger pinches. We also created a hand gesture set designed around coarse movement of the hand. We included a relaxed gesture as a neutral state to both gesture set, so one that has 5 gestures and the other one has 8. According to the result, we found that our highest accuracy in the wrist were in the wrist location, and also when using the hand gesture set. That condition achieved an accuracy of 96.6%. We compared this result to previous work which also used pinch gesture set, and overall, the accuracy compares favorably to methods such as EMG. Since most previous work use their own custom gesture set, it makes direct comparison quite difficult. So we compared our approach with them in terms of number of gestures supported and accuracy. As you can see in the picture, our approach has this great promise not only because it has high accuracies, but also support a large number of gestures. As any techniques, Tomo has its own limitations. First, we found a 50 kilohertz environmental noise, which is largely from the fluorescent light. That is partly why we select the 40 kilohertz to be the excitation signal to get away from this noise. And also, the power consumption for now is 50 millivolts, which has this great potential to be decreased in future. Finally, we tested cross-user accuracy and reproducibility in the study. As we discussed in the paper, we observed drops on the accuracies when our system was trained and tested with different users, and when it's taken off and reworn at a later time. This is very similar to what we see with other biosensing systems such as EMG and bioacoustics, and our approach is no different. However, more work is definitely required to overcome this limitation. I want to close my talk by offering one example use case. Since our approach didn't have a screen, we implemented a Samsung Gear smartwatch and developed 2 toy applications. In the first app, the user navigates through a list of messages, opening one with a grasping gesture and close it with a stretch. In the second app, when a phone call comes in, it can be dismissed with a quick flick of the hand, or it can be answered with a grasping gesture. For future work, we are actually currently working on the next version of Tomo. For most, we want to increase the resolution and use the reconstructed image to compensate for the electrode displacement, which we suspect to be the primary reason for the accuracy drops when the sensor is reworn. Also, want to use superior band ergonomics and the better electrode material to make the signal more stable. And want to use sweep frequency to make our setup more robust to the environmental noise. In addition, we are looking forward to exploring other applications leveraging the EIT system. We'll be holding a demo tonight, so please come to our table and take a look. Thank you.
Hi, Evan Suma from USC ICT. Very nice work. I'm wondering if this is limited to the detecting the activation of discrete gestures, or if it could be used for interpolation between two gestures in a continuous manner. For example, if you had a pinch closed and a pinched open, you could get the kind of continuous signal between them, you could do like a mid-air pinch to zoom.
Oh, good question. Actually, during our piloting experiment, we found that if we do this, with a closer distance, and do this, and with a larger distance, we can definitely observe a signal change. The impedance change, because we pull, even with this gesture, this little movement, we can still see the impedance change by measuring the cross-sectional impedance. The signal still exists. But if we include that feature into our gesture set, that will screw up our entire accuracy. but it's definitely possible. Yeah, it's possible. That's a short answer.
Mark Gross from University of Colorado Boulder Atlas Institute. So in your demo, the gestures you used were quite extreme. How small can you make the gestures and still have them recognized?
How small? I don't know if I understand the definition by small, because when we use pinch gestures, that's quite minor, because that involves only minor muscle movements. Is that what you mean by small? Or, yeah, go ahead. Yes. Yeah, we can still do that, because actually I can quickly switch back to the live demo. As we can see, even I perform a little gestures like that, we see the signal change, right? I'm not moving my hand very much, but still we see the signal change. The classifier is confusing only because when I trained the gesture, it doesn't know it can do this, right? But definitely we can see the signal change, so it's possible.
Hi, I'm Kirmani from Google. Excellent work, especially the end-to-end system implementation was very impressive. I have a question. So in building machine learning applications, you typically, when you only train using positive data, it's possible to achieve a very high accuracy and reproducibility. So typically it's a large negative data set is also used. So I'm curious, what type of negative data did you use in training while building your classifier?
So the question, let me repeat your question to make me understand more clearly. So your question is, what feature did I use and what classifier did I use, right? So for a short answer, yes, it will confuse the classifier if I combine pinch gesture together with hand gestures which involve gross hand movement. Yes, the short answer is yes. So I guess, yeah, I don't know if that answers the question, but the answer is yes.
Hi, this is cool work. Deepak Vambar into Labs. Does the system also work if you keep your hands at your side and kind of do it more discreetly? So let's say you kind of train like this and this is down. Can you put your whole hand down and then do like a down motion?
Oh, that's an interesting question, because during the previous experimenting, we found out actually when I raise my hand, the impedance rises, because we suspect that because the blood flush back, that which increase the impedance between the measurements. When I put it down, the impedance sort of increased, right? This definitely can hurt our classification. But if we let the classifier being exposed in more data, for example, let the user wearing this sensor for a year and train under different circumstances, then it can make our classifier more robust.
Eric Paulus, UC Berkeley. Thank you for doing a live demo. It's amazing. I'm curious, there's no reason this has to be on the wrist per se. You could train this, because I'm thinking of some future version of this that's so small it's almost embedded on, say, the ring of my socks. And so now my foot becomes this also interactive, a more discrete way of interacting. I don't see any limitations to that. Do you? I'm not sure. If you've looked at other parts of the body that you could do these measurements and training on.
Yes, this is actually it's a very interesting question. During the early experimenting, we tried to put it under my leg and try to put it around my neck, and definitely we see some interesting stuff going on when I do this, and when I try to run. Yeah, definitely. And also, yeah, we will be holding a demo tonight, and actually you can play around with the signal and see which part of your body create most interesting signal. Yeah.
All right, thank you.